So if you guys remember, when we deal with things in a radical, when it looks like this, we're talking about square roots. We can also have one that looks like this that would signify cube roots, right? If I have a square root, we're saying, what number can I multiply by itself to equal what's in there, right? If I'm having a cube root, I'm saying, what number can I multiply by itself 3 times to equal what's in there? If I have a fourth root or a fifth root, a fourth root says, like, what can I multiply by itself 4 times to see what's in there? So say if I have like the square root of 16, I know that 16 equals 4 times 4, right? And so I could say that the square root of 16 is 4, right? Technically plus or minus 4, right? If I have the cube root of 20, oops, I don't know, I'm losing my mind today. If I have the cube root, which means I have a 3 in here, of 27, I'm saying what number times itself 3 times equals 27? And I know that 3 times 3 times 3 equals 27. And so this would be 3. If I have a fourth root, I'm saying what number times itself 4 times equals 16, right? And I could go, okay, well, 2 times 2 is 4 times 2 is 8 times 2 is 16. So 2 raised to the 4th power would equal 16. So I could say this is plus or minus 2. Notice when my roots are even, my solution is plus or minus, right? When my solution is odd, it's 3. Now, if I had, what is the cube root of negative 27, my solution would be negative 3. And there's a difference with odd indexes and even indexes in that if I look at 16, I know that negative 4 times negative 4 also equals positive 16, right? But if I look at 27, if I have negative 3 times negative 3, I get positive 9 times another negative 3. It would give me a negative 27. No, you don't turn the notes in, Maria. And so that's kind of how that goes, right? So if an odd numbered index right here is there and there's a negative in here, you know your solution is going to be negative. If it's positive, you know your solution is going to be positive. One of the things that really helps to know is your perfect squares and your perfect cubes. So some perfect squares would be, let's see, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 25, 36, 7 would be 49, 8 would be 64, 9 is 81, 10 is 100, 11 is 121, 12 is 144. I could keep going, but I'm not going to. Perfect cubes, right? So perfect squares, we're saying 1 times 1, 4 times 4, 3 times 3, 4 times 4, I'm sorry, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6. Perfect cubes, we're going 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4. Now I have to look. 5 times 5 times 5, 6 times 6 times 6, 7 times 7 times 7, Notice our numbers are going up much higher, much faster, right? And we could keep going. Dot, dot, dot. Perfect fourths. Gosh, I don't even know if I know any of these. Let's think about, well, one is obvious. 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2 is 16. 3 times 3 times 3 times 3 is 81. 4 times 4 times 4 times 4 is 256. 5 times 5 times 5 times 5, 625. And then I think we've got like 1296, and I can't think of any more off the top of my head. What's good about knowing these, or at least having a list of them in front of you when you're trying to break these things down, is it gives you a good idea of, one, how big, when we have a power, as the powers change, how much faster things increase, right? Let's talk about square roots, though, a little bit, about radicals. This right here is the radical sign, right? That one's going up a little bit. I don't like it. Let's go this. Right here is the radical sign. Right? It looks like a division sign, but with a little thingy right here. This, whatever number is in here, we call the index. What we call the bit that's in here is the radicand. Ultimately, what we're saying is, what number can we raise to this power to get what's underneath, right? And if we wanted to look at things in terms of the radicand, like say I have the cube root of 27, I can actually take that out of the radicand and write it as 27 to the 1/3 power, right? If I have the square root of 16, I could write that as 16 to the 1/2 power, right? That's all these square roots are, is their inverse of exponents. What is the importance of this? Nothing for right now. If you don't have an index written in, then it is 2. If there's nothing written right here where the n is, then it's 2. We don't write 2 for the square root. We just know it to be true. So if I have the square root of 16, we know that we have plus or minus 4, right? Because 4 times 4 equals 16, but -4 times -4 also equals 16, right? And so we know that each of these would give us 4. So we would know we could do -4 or +4. I could probably switch those around. So I think I've done plenty of examples in that respect. There's some things that it helps to know. I wish I could do like a box of stuff. I wonder if I can on this. If I can insert. Oh, I can. Well, that's not what I'm looking for. I don't want a note grid. I just wanted a regular old grid that I could put in. Oh well. So say I have an index, right? Or n. And then I have a radical. which is the number underneath, right? And then I have type of root. And I have number of real roots. Number of roots. So this is kind of what I was saying before. If my index, if my n is even, right, my radical has to be positive. What is the radical? My radicand has to be positive. The radical has to be positive. So this has to be positive for it to work, right? If it's even, right? And so we've got, if the radical is positive, then I have real roots, and I have two of them, right? The plus and the minus. If my index, if my n is odd, and I have a positive radical, my solutions are still real, but I only have one root, and it will be positive. Again, if my index is odd, right? So we're saying to like the cube root, like a 3 would be odd. And the radical itself was negative, I would have a real solution, and I would have 1, and it would be negative. Next, if we have an even with a negative under the radical, we would have an imaginary. And we would still have two solutions, one positive and one negative, which you guys probably remember from quadratics when we were getting into complex numbers. If we had a negative underneath the radical for a square, right, we had the imaginary numbers. We had to pluck the I out. Well, that's true no matter what the n is, if the n is even. Simplifying radicals is nothing new. We have talked about this. We just haven't done it with greater powers. If I have the square root of 117, I'm going to look at the things that make up 117. And I know that 117 is 9 times 13. And though 13 is a prime number, 9 is a perfect square, right? It's 3 times 3. So I could rewrite this as plus or minus 3 times the square root of 13. If I have, so I have something like 4 times the square root of 320. Well, if I look at that, I'm going to go, well, I've got 4 times this square root still, but I can break up 320. First of all, it's I think it's 64 times 4. 64 times 5. It's 64 times 5. And 64 is 8 times 8, right? It's a perfect square. So I would have 4 times 8, right? Plus or minus 8. Times the square root of 5. Can pull out the square root of 5. And we would have 32 radical 5. And they're not always going to be square roots. The lucky thing for you, though, is when they're not square roots, they tend to keep the numbers smaller just because otherwise they get out of control. Hard to deal with. So if I have, for example, 2 times the cube root of 48. I'm going to look at the cube root of 48 and what that is going to break down to be. Now, if I look at 48, I know that it is, well, it's 6 times 8, right? But I know that 8 is 2 times 2 times 2, right? It's a perfect cube. So I could write that as 2 times 2 times the cube root of 6, which is 4 times the cube root of 6. Does that make some sense to you guys? All right. I'm not going to get into anything that breaks down much differently than that. As they get bigger, keep in mind, we're not going to go too big with any of it because the numbers, to the fourth root are going to get astronomically large. But sometimes you're going to have variables in there. And actually, dealing with variables when we're talking about square roots is pretty easy because you know how many of them there are. So if I have the square root of 32 x to the fourth y to the ninth, this is a square root. It's how many pairs of something can I take out? And I could write this as, well, I've got 16 times 2, and I like breaking it down that way because 16 is a perfect square. I've got 4 x's, right? This is x times x times x times x. And this is times y times y times y times y times y times y. Oh my gosh, why did I do this one? 1, 2, 3, 4, 5, 6, 7, 8. I was almost there. 9. I don't have to write these out. I can look at this and go, well, I have 16 is a perfect square. It is 4, right? Plus or minus. 2 does not match. Doesn't have a match, so it can't come out. But I have 2 sets of x. I have x and then another x that I can pull out. So I can pull out x squared. Here I have 1, 2, 3, 4 pairs of y. So I have y to the fourth. And then anything that's left goes under, right? We pulled that out. So we've got 2. We don't have any x's left, but we have 1 y left, right? And that's how we're going to solve things like that. But you don't have to write it out that way. You can just look at it and go, say I have the square root of 324, a to the third, b to the seventh, right? Well, the square root of 324, I'm just going to tell you right now, is 18. It's 18 times 18. So I can pull out 18. I have 3 a's, right? I can pull out 2 of them, right? When I pull out 2 of them, I write it as a over here. B, I have 7 of them. When I divide that by 2, right? I have b to the 7th power. If I divide 7 by 2, I wind up with 3 and a remainder of 1, right? So that means I can pull out 3 sets of b's. I have to put back under anything I couldn't pull out. Now, 18 times 18 is 324. There's nothing left under there number-wise. I pulled out 2 a's, but I still have an a left. I pulled out 6 of these b's, right? 3 sets. But I'm still left with 1 b underneath. Did that help, Sam? Did that help with the explanation a little bit? Because I saw your I want to make sure that you got it. Yeah. I'm going to do one with a cube root, and then I will let you guys go. So if I have the cube root of 216 m cubed n to the 6. Think about this now. This third power, right? This 3 of my index says I need 3 of something to pull it out, right? To be able to factor it out. Now, if we go up to our chart that I had at the beginning here, where did it go? Where I wrote all those perfect cubes. Notice that we have one here at cubes for 216. It's 1, 2, 3, 4, 5, 6 cubed. I just heard the weirdest sound. It freaked me out a little bit. So what that's saying to me is that 6 times 6 times 6 equals 216. So I know that this part can come out as a 6, right? And we don't have anything left. It's a perfect cube. M, I have 3 of them in here. That's how many I need to pull an M out. N, I have 6 of them, right? Which is 2 sets of 3. So I can pull this out as N squared because it's saying that I have 2 sets of 3. There is nothing left under this cube root. I lied. I'm going to do one more. I want one that's not perfect. But this one, I promise, will be the last one. If I have a cube root of 56, hold on, this is r to the 8th, s to the 4th. R to the 8th, s to the 4th. When I look at this, 56 is 7 times 8, right? 56 is, if I look at 56, it is 7 times 8. 8 is a perfect cube, right? It's 2 times 2 times 2. So I can pull the 2 out, but the 7 is going to have to go back because I can't break it down. The 8 is 2 times 2 times 2, so I can pull those 3 2s out. That takes care of my numbers. R, I have r to the 8th power. For every 3 r's, I can pull 1 out. So I have r to the 3rd would be 1, right? And then I can do it again, which would give me r to the 6th, so that's 2. But then I am still left with 2 r's. Here I have s to the 4th, so I could pull 1 set of 3 out, but I still have 1 left. If it helps, like the 56, I can't help you with much, right? We just know that it's 2 times 7, right? So if we look at it's 2 times 2 times 2 times 7, right? R to the 8th, that's r times 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 r. How many do I have there? Good. And then I have s to the 4th, s times s times s times s, right? That's ultimately, if I broke that whole thing down, that's what it would look like, right? I'd have all of these things in their smallest component times each other, right? S to the 4th means that I have 4 s's multiplied together. R to the 8th means that I have 8 r's multiplied together. Right? We broke that down to its basest thing. And every time I have 3 of something, I can pull it out. Right? 7, I only have 1 of those, but here I have 3 r's, so I can pull out an r. Oops, I have another set of 3's of r's, so we'll call that squared. I only have 2 left, so I can't pull that out. Here I have a set of 3 S's. And now I'm going to be left with whatever I couldn't pull out. So we have 7, 2 R's, so R squared times S. Hopefully that was a little better in the explanation when we broke it down. Play with these a little bit. Your homework is in Delta Math. You can keep going till you have 100% on these, right? There's nothing to stop you from doing that. I don't have any penalty on there. So you can keep doing problems till you get them all correct. There's no reason to ever not get 100% on Delta Math. But yeah, any questions about any of this? Does it feel okay? Do you feel like you need to play with it a little bit before you have questions to ask, or do you have anything specific that I could help you with? Sam's got it down. Mashka's good. All of your stuff is already posted in PowerSchool. I'll be posting this video as well in just a minute. If you have any questions, make sure and ask them. I will not be available for tutoring this afternoon because I have an IEP meeting for the rest of the day, 2 hours. That's a really long time. But I do have time tomorrow. I can always make some time tomorrow if you guys need any help. All right. Otherwise, it was good to see you. I hope you have a good day. I guess I could stop recording all of this.